Hello everyone, I am Ojis Sharma, student of Symbiosis University of Applied Sciences. Today presenting you a video presentation on the topic half adder and full adder from the subject Computer Organization and Architecture. First let's look at the contents we are going to cover in this presentation. So first we will see the definition of both the adders. Although there are different types of adders, but in this video presentation we are only focusing on half adder and full adder. Then we will see their truth tables. From the truth tables we will draw the K-maps for sum and carry of both the adders. From the K-maps we will obtain the logical expression. Then we will see the gate diagrams of both the adder, and at the last we will see the difference between half adder and full adder. So let's get started. First let's discuss about half adder. Half adder is a combinational logic circuit which takes two inputs and gives two outputs. It is designed to add two single bit binary number and generates a carry and a sum. Here is a block diagram of half adder. The two inputs are also known as augend and addend. Augend is that value in which another value is added, while addend is that value which is going to be added into another value. Now, as definition says, half adder takes two inputs and generates two outputs. Half adder can pass sum, but it is unable to pass carry into next adder. Hence, it is used in calculators, digital measuring devices, etc. Now let's see the truth table of half adder. A half adder has two inputs A and B and two outputs sum and carry. When both of the inputs are 0, then the sum and carry becomes 0, and when one of the two inputs is 1, then sum becomes 1 and carry remains 0. But when both the inputs becomes 1, the sum becomes 0 and carry becomes 1. Here we obtain the outputs using laws of Boolean algebra. Now let's see how we will obtain the outputs using logical circuits. For that, let's draw the K-maps. First, we are going to draw K-map for sum in half adder. Let's place the inputs of A on left hand side and inputs of B on the top. Here A is the most significant bit and B is the least significant bit. Now place the outputs according to truth table. Here you will observe that the high output values are placed diagonally. Therefore we are unable to group them. So we will mark them separately. Now let's draw the K-map for carry in half adder. We will follow the same procedure as we done previously. Now place the outputs of carry into K-maps according to truth table. Here you will observe that there is only one high output value. So we will mark it. Now let's obtain the logical expression using these K-maps. First, for sum we will write A complement dot B plus A dot B complement, as the high output values are obtaining in K-map only when A is 0 and B is 1, or when A is 1 or B is 0. From this expression, it is observable that the expression is of XOR gate. So we will write A XOR B. For carry, as there is only one high output value when A is 1 and B is 1, we will write A dot B, which is the expression of AND gate. Now let's see the gate diagram. Here is a gate diagram of half adder, which consists of one XOR gate and one AND gate, having two inputs A and B and two outputs sum and carry. Now through animation, let's see how logical circuits generates the desired output. When A and B are 0 means no current is flowing through the circuit, then sum and carry will be 0. But when B becomes 1 means current is start flowing from input B and A remains 0, then XOR gate makes the condition true as inputs are opposite, and hence at sum output will generate as 1. and AND gate makes the condition false as both the inputs are not high. So at carry, output will generate as 0. If we toggle the input, means A becomes 1 and B becomes 0, then still the obtained output would be same. But when both input becomes 1, then XOR gate makes the condition false as both the input becomes same, hence generating output 0 at sum, and AND gate makes the condition true as both the inputs are high, hence generating output 1 at carry. Now let's discuss about full adder. Full adder is a combinational logic circuit which takes 3 inputs and gives 2 outputs. It is designed to add 2 single-bit binary number plus carry-in digit to produce a sum and a carry-out digit. A half adder is unable to pass carry into next adder. So, we combine 2 half adders to get a full adder which has the ability to pass carry into next adder as an input. When we use multiple full adders in different combinations, then they become some special adders. Here is an example. Here is a diagram of carry ripple adder in which full adders are arranged in such a way that 2 inputs are passing parallelly and carry out digit of one adder is passed serially as an input for next adder. Full adders are used in digital circuits, microwaves, computers, and etc. Now let's see the truth table of full adder. A full adder has 2 inputs A and B and carry-in digit named as CI and 2 outputs which is sum and carry or carry out or CO. When all the inputs are 0, then we get sum and carry as output 0. When one of the 3 inputs is 1, then sum will be 1 and carry will be 0. When 2 out of 3 inputs are 1, then sum will be 0 and carry will be 1, and if all the 3 inputs are 1, then we get both sum and carry as output 1. Now from the truth table, let's draw the K maps for sum and carry in full adders. First we are drawing the K map for sum. So we will place the inputs of A on left hand side and inputs of B on the top in 4 combination, that is 0 0, 0 1, 1 1 and 1 0. Here A is the most significant bit and B and Ci are least significant bits. The terms are not arranged in numerical sequence as only one input value can change its value which moving horizontally. Now place the outputs of sum according to truth table. Here you will observe that high output values are placed diagonally, thus forming a checkerboard configuration. So we will mark them separately. Now let's draw the K map for carry. We will follow the same procedure as we done previously. Now place the outputs according to truth table. Now there is a grouping, so we will group the outputs of inputs 111 and 110. Then we will mark the remaining 2 high outputs separately. Now let's obtain the logical expression using these K maps. First for sum we will write a complement dot b complement dot ci plus a complement dot b dot ci complement plus a dot b complement dot ci complement plus a dot b dot ci. Now in this expression each value is repeating twice and also containing its complement. From this we will write a's or b's or ci. Now for carry we will write a complement dot b dot ci plus a dot b complement dot ci plus a dot b. Here in this expression the first 2 terms belongs to those 2 high outputs which were marked separately. Now if we see the grouped outputs, then we will observe that only ci is changing its value in that grouping. So we will neglect ci and hence the third term will be obtained as a dot b. Now By taking Ci common from the first two terms, the expression will be a dot b plus Ci dot a XOR b, or a and b or Ci and a XOR b. Now let's see the gate diagram. Here is a gate diagram of full adder, which is consist of two XOR gate, two AND gate and one OR gate, which are arranged according to logical expression we obtained in previous slide. It has three inputs A, B and Ci, and two outputs sum and carry or CO. When all the inputs are 0, then the both outputs sum and carry will become 0. When Ci becomes 1, means the carry input takes high input from the previous adder. Then the current starts flowing through second XOR gate and second AND gate. The second AND gate stops the current, hence generating the output 0 at carry, while the second XOR gate allows the current, hence generating the output 1 at sum. When B becomes 1 and A and Ci becomes 0, then the current starts flowing through both XOR gate and both AND gate. The both AND gate stops the current, hence generating the output 0 at CO or carry, while the both XOR gate allows the current, hence generating the output 1 at sum. When both B and Ci becomes 1 and A becomes 0, then the second XOR gate stops the current, hence generating the output 0 at sum, while the second AND gate allows the current as both the inputs are high, which further passes through OR gate, hence generating the output 1 at carry. When A becomes 1 and both B and Ci become 0, then the both XOR gate allows the current, hence generating the output 1 at sum, while the both AND gate stops the current, hence generating the output 0 at carry. When both A and Ci becomes 1 and B becomes 0, then the second XOR gate stops the current as both the inputs are same, hence generating the output 0 at sum, while the second AND gate allows the current, which is further passes through OR gate, hence generating the output 1 at carry. When both A and B becomes 1, then the first XOR gate stops the current, hence generating the output 0 at sum, while the first AND gate allows the current, which further passes through OR gate, hence generating the output 1 at carry. When all the three inputs becomes 1s, then the first XOR gate stops the current, but the second XOR gate allows the current, hence generating the output 1 at sum, while the second AND gate stops the current, but the first AND gate allows the current, which further passes through OR gate, hence generating the output 1 at carry. Now let's see the difference between half adder and full adder, which you also can say the quick recap of our whole video presentation. The half adder is designed to add two 1-bit digits, while the full adder is designed to add three 1-bit digits. The previous carry bit is not used in half adder, while the previous carry bit is used in full adder. It consists of one XOR gate and one AND gate, while a full adder is consists of two XOR gate, two AND gate and one OR gate. The logical expression for sum is A XOR B and for carry is A and B in half adder, while the logical expression for sum is A XOR B XOR Ci and for carry is A and B or C and A XOR B in full adder. A half adder is used in calculators, digital measuring instruments, etc. as we know, while a full adder is used in digital processors, multiple bit additions, computers, microwaves, washing machines, etc. Thank you for watching. I hope you enjoyed this video and this presentation would enhance your knowledge.